Hello and welcome. In this video, I'm just going to give you the solutions of the structural formulae, molecular formulae, and condensed formulae of the substances that I asked you to go and solve in the last lesson. So the first one that we're going to give is that of butane. Now, butane is an alkane, as you can hear from the name, and you need to remember that as an alkane, its ending must be ANE, and but corresponds to an alkane, which is a hydrocarbon, which has got four carbons. So you would need to show the four carbons. You also need to remember that around each carbon there are four bonds that will be formed because carbon is tetravalent, right? So you would show that around each carbon there are four bonds. Remember, in an alkane, the functional group is a carbon-carbon single bond, so there cannot be any double bonds in the structure. And because you are dealing with hydrocarbons, if you are going to now draw the structural formulae of butane, which is a hydrocarbon, you are only going to have carbon and hydrogen atoms only, nothing else. So all that you are going to be adding here are the hydrogen atoms. If you do not add the hydrogen atoms, that will be considered incorrect. So you can't just leave it as open spaces and assume that whoever is reading or marking the work will know that it's a hydrogen that's supposed to be there. And then the molecular formula for the butane, you count again how many carbons do you have. You've got 1, 2, 3, 4 carbons, so it's going to be C4, and then count the number of hydrogens which you have. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's C4H10. And then the condensed formula, remember what we said about the condensed formula, that you count the number of hydrogens that are bonded to each carbon that you have. So in this case, you have on the first carbon, you've got 3 hydrogens, so CH3. And then on the next carbon, you've got CH2, and you've got 2 CH2 groups that follow each other. So you can put that in brackets and show that there are 2 of them. And on the next one, you'll have a CH3 group as well. So you've got CH3 and bonded to it, you've got 2 CH2 groups, and then you've got a CH3 group that is bonded to it as well. All right, so then the next one is your pentane. Your pentane, let me just create space. I'm just going to move this to the left, right? So for your pentane has got how many carbons? Got 5 carbons. So 1, 2, 3, 4, 5. So make sure you've counted 5 carbons, and then around each carbon is tetravalent, so 4 bonds around each carbon, and it's a hydrocarbon as well, so there are no other bonds other than the simple carbon-carbon double bond. So, and each one of those spaces is occupied by a hydrogen. So you've got 1, 2, 3, 4, 1, 2, 3, 1, 2, 1, 2, 1, 2, and then that's it. So count the number of hydrogens to get the molecular formula. So this is the structural, and then the molecular. It's how many carbons do we have? You've got 5 of them. So you represent the 5 as C, so the formula C5. and then how many hydrogens? H, and then they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the condensed formula, you've got your CH3 for the first carbon, CH3, and then you've got 1, 2, 3 groups of CH2s. So you've got CH3 and then 3 groups of CH2. So you put that into the brackets and then show that there are 3 of them. And then on the last one, you've got another CH3. So CH3, CH2 times 3 groups, and then you get your CH3. So that is your pentane. Then the next one that you have is the hexane. Hexane has got 6 carbons. So now with the 6 carbons that are available, you would draw the structure with 6 carbons. Count 1, 2, 3, 4, 5, 6, and then from there you would add in the hydrogens by completing the tetravalency around each carbon. Oops. So that's on the carbon. Very important that you count, because if you don't count, that will be marked incorrect. So there you go. Count the number of carbons that you have. So you've got C6, and then count the number of hydrogens that you have. You find that you've got 14, C6H14, and then the condensed formula is going to be your CH3, and then have a look at this. How many CH2s do you now have? So CH2, and then you will discover they should have 4. 1, 2, 3, 4. So you now have 4, and then the CH3. In the previous one, if you looked, so yeah, for carbon number, with this one you've got CH3, and then CH2, 3 of them, and now you've got CH2, 4 of them. So in the previous one, you should have had CH2, 2 of them. And in the previous one, you just had 1 of them. And you see that. So that is basically how you look at that. So there's a difference of a CH2 from one to the next as you increase the number of carbons in a homologous series. So another important thing that you should be aware of is that there is the general formula. So here you find that you've got C5, H12, CH4, etc. What you are looking at is the general formula for an alkane. Is Cn, where N is the number of carbons, and then H2N plus 2. So Cn, so the N is the number of carbons, 2N, so if I've got 5, and then 2 times 5 is 10, plus 2, this would give me a total of 12. So the general formula is CnH2n plus 2. And then further down, we also asked you to give the formulae for your pentene, as we did in the previous one, your butene, etc. We had also not given you the general formula, or the condensed formula. The condensed formula for your alkene. So for now, we're just looking at the alkene. Here you'll have your CH2, CH2. And then the next one, you'll have your CH2, and then CH, and then CH3. Right, CH2, CH, CH3, and then the next one, I've got CH2, CH, and then CH2, and then CH3. And then the next one, I've got CH3, or the isomer of that will just be CH3, CH, CH, and then CH3. And for your pentene, for the pentene, right, the possible outcomes or the possible structures that you'll get is one where you'll have your carbon, double bond, carbon, then count the number of carbons, 1, 2, 3, 4, and then what you will then add are your hydrogens, 1, 2, 3. I've put too many, 1, 2, 3, 4. 1, 2, 3, one more, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this becomes an H. Count 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And the formula would be C, 1, 2, 3, 4, 5, C5, and then this should be H10. Count 2, 4, 6, 8, 10. And the general formula, or no, the condensed formula would be CH2 for this particular one, CH2, and then CH, and then CH2, CH2. So I've got two of them, and then CH3, right? But this is not the only way of representing the formula for pentene. This is pent, so the actual name for this would be pent 1-ene, because the double bond is on carbon number 1. It is possible that we could have had the double bond on carbon number 2, between 2 and 3. And then from there, you would then say, okay, this is carbon number 1, that's carbon number 2. And then that would be carbon number 3. So the the formula, the structural formula would look something like this: 1, 2, 3, and then one more here, 4, and then 1, 2, 3, and then one more here, 4, and then 1, 2, and then 3, and then 4, and then 1, 2, 3, 4. So in this case, the formula for that compound would be your, so it's on carbon number 2, so it's pentene, but with the carbon, the functional group on carbon number 2. So it'll be pent carbon number 2, where that's where the functional group is, and that functional group is found on carbon number 2, and then it's going to be your ene ending that there. So pent 2-ene, that's where you're finding the double bond on carbon number 2. And you can do the same thing. You would write the chemical formula is still going to be C5H10, and then the condensed formula will be CH3 on that first carbon, then CH, and then on carbon number 2, carbon number 3, you've got CH as well, and then carbon number 4, you've got CH2, and then on carbon number 5, you've got CH3. Check the 1, 2, 3, 4, 5, then 3, 4, 5, 6, 7, 10. So it's still the same number of carbons, and then from there you would have given us that arrangement, right? So likewise, you can conclude or continue with the hexene, heptene as well. But some other food for thought: is this the only? Are these the only formulae that, or isomers? Remember, we call these isomers. Are these the only possible isomers for pentene? No. The answer is no. There are other isomers, but we're going to talk about that in the next video when I talk about isomerism. But for now, it's important that you are able to identify this type of isomerism, which we shall elaborate on further, but this is referred to as the position isomerism. Where is the position of the functional group? So it differs, and because of that, it's going to have different structures. All right, and it's also going to have the different properties depending on where the functional group is. Right, and then so for your hexene, you would have something similar. Let me quickly move this here just further down, cut this here and move it. I'm just going to move this somewhere here. Right, so hexene, with your hexene, what you're going to get, again, 6 carbons. Just going to put it here, 6 carbons, 1, 2, 3, 4, 5, 6, and we are going to be sticking with the straight chains. There's a double bond. Let's, just for argument's sake, let's now count from the right. Right, so there's going to be a double bond here. So this becomes carbon number 1, and that's number 2 going that way. So we now have 1, 2, 3, and then the 4th carbon, and 1, 2, 3, 4, 1. So that becomes too many, so we've got to erase that there, right? So that we don't violate the tetravalency of carbon. So count the number of hydrogens: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So and then our formula would be C6H12, and then our condensed formula, so it will be CH2, just counting from there, CH, carbon number 2, and then carbon number 3, I've got 1, 2, 3, 3 CH2s, and then CH3, right? So that's my carbon number 1. Remember, when we counted, we said that's carbon number 1, that's carbon number 2. Why did I call this carbon number 1? Because that's where the functional group is found. So if the functional group is found here, then we know that this is carbon number 1. So if the functional group is found here, then we know that this is carbon number 2. Why did I call this carbon number 1? Because that's where the functional group is found. So if the functional group is found here, then we know that this is carbon number 2. we're going to look at the carbon that is attached to it must have the smallest number possible. So this is the first carbon, so it becomes carbon number 1. Or you could have had the same carbon, another formula or structural arrangement for that would have been this 1, 2, 2, 2, 3, 4. So there's the double bond here and the other one there. So now the double bond has moved to that next carbon. So this becomes carbon number 1, that's number 2. And that will be number 3. And so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So they are your hydrogens. No, this is too much. I've put in too many hydrogens here. Remember, there must always be 4. 1, 2, 3, 4, 1, 2, 3, 4. Again, this is carbon number 1, number 2. So when you name this, this is going to be 1. This is going to be carbon 1, 2. So it's carbon number 1. So, and it's got 6 carbons. So it's hex 1 in. And then this other one is this is carbon number 1, that's carbon number 2. So it's hex 2 in. So this here is hex 2 in. Again, these two are what? Are isomers. Right? And what type of isomers? Position isomers. Can we have another position isomer? Yes, we could have another position isomer. Where? Well, if the double bond is moved from where it is and then it comes to carbon number 3. So 1, 2, 3, 4, 5, 6. So it doesn't matter now which way you count from. Carbon number 3 will be number 3. So this is 1, 2, 3. That's where the double bond is. Or if I count it from here, that'll be 1, 2, 3. The double bond is still on the carbon number, which is numbered number 3. All right. And so from there, you would count 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then just add up all your hydrogens. Make sure that you have counted correctly. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Right? And therefore, this is what you have. So this, remember we said, it doesn't matter from which side you count from. If you count from here, that's 1, that's carbon number 2, that's carbon number 3. So carbon number 3, that's where you've got your bond, your your double bond. So it's going to be your hex 3 in. And these are all isomers of the same species. So now, meaning to say, the longer the chain becomes, the more isomers you're going to receive. And in this particular case, I'm just only referring to your position isomers. We will even see later on when we start looking at the branching. Is it going to be a straight chain, or is it going to be branched? Are there going to be substituents that are added to that particular compound? So as far as this is concerned, I hope it makes sense. That if you've got comments, please share your comments, pass it on to your friends, share it, like the channel, and See you in the next one when we look at isomerism.